Good day and welcome back for the first part of our discussion on integration strategies. We are now in a fantastic position when it comes to integration. We've covered the main techniques of integration that we're going to be talking about, and it's now all about building up the thought process or the intuition involved when it comes to deciding what is the best approach to evaluate a given antiderivative. And when it comes to anti-differentiation, an observation we've made previously is that it's not as straightforward as differentiation can sometimes be. And what I mean by that is when it comes to differentiation, it's very mechanical. You look at a function based upon its form, whether it's a product, a composition, a quotient, you have a differentiation rule that we can immediately apply. With anti-differentiation, that's not always the case. If you look at a given antiderivative and you immediately know how to evaluate it, that's perfect. It's the ideal scenario. But if not, what we would like to have is kind of a mental process or checklist that we go through, which is the goal of this section. And one of the most important things you can do is practice examples. And I realize that I most likely sound like a broken record as I keep recommending that we go to the suggested problems. In fact, this section in the textbook contains 82 integrals that need to be evaluated, which means 41 of them are odd, and you can find answers in the back of the book. So there is no shortage of good practice problems to be found. So let's go ahead and get this discussion started. When it comes to evaluating integrals, we have common antiderivatives, which are the most frequently encountered, and these are formulas that we should all be quick, familiar, and efficient with. And note, some of them are formulas we've been using since Calculus 1, whereas others of them, for example, the antiderivative of secant, or 1 over x squared plus a squared, or even just an exponential a to the x, are formulas that are new to us this semester. So make sure you are familiar with these common antiderivatives. So for the purpose of discussion, suppose we have an antiderivative that we would like to evaluate. It's not a common antiderivative, and we are unsure as to what approach to take. What I would like us to do is walk us through kind of a checklist that gives us suggestions. And remember, if at any point along the way you come up with a method of approach, that's the goal. You stop, you evaluate. So the first question we might ask ourselves, is it a standard integral, so one of these common formulas above, or a modified version? And what do we mean by this? Well, for example, you could have something as straightforward as, say, e to the 5x, which you may look at right now and immediately know what that antiderivative is, but note it's just a slight modification of one of these common formulas. So in this case, you would use the substitution u equals 5x, or you just might recall from our experience that the antiderivative of e to the kx, as long as k is a non-zero constant, is 1 over k e to the kx plus c. Or similarly, we may have an integral of the form 1 over the square root of 4 minus x squared. And note, if we think about evaluating this, you definitely could apply a trig substitution, but we do want to be efficient if we can. And note, we can algebraically manipulate this slightly to get it back to a standard integral. If you pull a 4 out of the quantity in the square root, you'd be left with a 1 over x squared over 4. And if we go ahead and pull that 4 out of the square root, you can make it a 1/2 in front of the integral, and then what you are integrating would be the square root of 1 minus x over 2 squared. And you're in an ideal scenario to do a u substitution with u equals x over 2, and then comparing it to this common formula related to the inverse sine function. The next thing to think about would be, can we simplify the integrand? Sometimes the simplifications are straightforward, other times they're a bit more subtle. So let's look at a few examples. If we are asked to integrate something like 1 plus e to the x squared over e to the x. There are several approaches, but I think one very efficient approach is to just algebraically expand in the numerator. 1 plus 2e to the x plus e to the x squared. And once we have done this simplification, we can simply break this up into 3 separate integrals. So I will leave it as e to the minus x plus 2 plus e to the x, but note each one of these functions are very reasonable to antidifferentiate. Or you might have something like x squared over x squared plus 1, which we have encountered somewhat frequently, which is an improper rational function because the degree in the top is equal to the degree in the bottom. And there is a subtle algebraic manipulation we can do to simplify the integrand. We could simply do the plus 1 minus 1 trick to rewrite this integrand as x squared plus 1 over x squared plus 1 minus 1 over x squared plus 1. And immediately we have a very reasonable integral that we can evaluate. You would also want to look for or try any obvious substitutions. So an obvious substitution, I would say, is when you can very clearly see some function derivative pair. In this case, if you were to let u be arctangent, then its derivative, 1 over 1 plus x squared, would play the role of du. Similarly, if we had something like e to the 1 over x divided by x squared. This is an ideal scenario, once again, for a u substitution, and our best guess for u is something inside of another function. So maybe our first attempt would be to say u equals 1 over x, so that du is minus 1 over x squared. And our integral in terms of u is now minus the integral of e to the u du. And at this point, if we're trying to evaluate an antiderivative that's not a standard integral or a modified version of it, the integrand doesn't have any maybe obvious simplifications or no obvious substitutions that are jumping out at us. The next thing to do is to go through the list of kind of the standard forms that we've encountered. So let me give you some quick reminders. Is it a trig function? In section 7.2, we discussed methods of integration for integrals involving sine and cosines to powers, or tangents and secants to powers. The next thing you might want to think about, is it a rational function? If it is a rational function, we will want to think about our techniques from 7.4. Is it a proper rational function? If so, try a partial fraction decomposition. If not, use a polynomial division or some algebraic manipulation to rewrite it. Is it one of the standard forms that we've encountered where integration by parts will apply? And recall what those forms are. It could be something like x squared, or really any polynomial, times an exponential. And note, it doesn't have to be just e to the x, it could be e to any constant x. Or things of the form x times a trig function, or really x times any function might make us think of integration by parts. Maybe an exponential times a trig function, or one of the inverse functions. Natural log of x, arctangent, arcsine, arccosine. These are all examples of functions which are well suited for integration by parts. Or, does your integrand contain an expression of the form a squared minus x squared, a squared plus x squared, or x squared minus a squared? If you see one of these three expressions appearing in your integral, that may prompt you to think about a trig substitution, and our discussion from section 7.3. And a slightly more subtle example of this we encountered recently in our discussion of PFDs and rational functions was integrating something of the form 1 over x squared plus a squared quantity squared, which could arise as part of a partial fraction decomposition. And at this point, if we still don't have a method that we found that works to evaluate an integral, we don't give up in frustration. We just keep going down our list looking for different approaches. So the next thing we would think about is, what about a more subtle substitution? For example, we've encountered the following scenario, I believe, multiple times. If I wanted to anti-differentiate e to the square root of x, I most definitely cannot do this directly. But what we can observe is that the troublesome part of this integral is because of the square root of x. So you might think, how about we substitute that away? So if u is the square root of x, we could say x is u squared, and dx is 2u du. So rewriting our integrand, we would have a constant 2, e to the u du. And now, what technique of integration applies? Integration by parts. Which is a perfect transition, because if you do not see a subtle substitution, just ask yourself, can you try integration by parts? Sometimes it may not be obvious at first, but if you have two functions being multiplied together, maybe you can make it work. And if you're still unsure, we may need to algebraically manipulate the integrand, which is most definitely something we've discussed and seen many examples of. And you don't have to go through this list in a linear order. You may look at the example and immediately from your past experience say, oh, I need to perform X algebraic manipulation. For example, if we had something like the antiderivative of 1 over the square root of x squared minus 2x. At first glance, it's not obvious how we would approach this integral. It doesn't directly compare to any of our common antiderivatives. There's no obvious manipulations, substitutions. It's not quite any of our standard forms. I don't think I would want to try integration by parts. But note, similar to things that we saw back in 7.3, we can complete the square underneath that square root. So if we complete the square, and I will let you do the algebra, you can rewrite this as follows. Underneath the square root, it would be x minus 1 squared minus 1. And this is a scenario where we can apply a trig substitution. We would let x minus 1 be equal to 1 secant theta, where the 1 is the a value, where 1 is a squared. So once again, the experience we get from practicing suggested problems, working through the class notes and worksheets, is extremely valuable for future problems. One last example. What if we had something like e to the x over e to the x plus e to the minus x? At first glance, this is once again kind of a troublesome integral. It doesn't really appear to fit any of our common forms. And when I find myself in this scenario, something I like to think about is, why is this a difficult integral? And in this case, the difficulty really hinges upon having both an e to the x and an e to the minus x in the denominator. So what we are going to do is multiply by 1 in a fancy way, so that we can make it easier for us to handle. And what I'm going to do is multiply by e to the x over e to the x. And if we multiply this by e to the x over e to the x, note our numerator will be e to the x times e to the x, and we have a dx. And our denominator, when the e to the x distributes through, is e to the x squared plus 1. And now this is a, hopefully, much more familiar looking antiderivative, in the sense that we might see a u, and if e to the x is equal to u, du is e to the x dx. So we have du, and then an extra u. So very quickly, we have a very reasonable antiderivative to evaluate. And note, to finish this up, you would have to keep going and do another substitution. So in this case, you might say, let w be u squared plus 1. And my reminder at this point is it is extremely reasonable, as we have seen, to have to use multiple methods of integration in the same problem. And let me finish with just one last easy piece of advice. When it comes to evaluating integrals, you have to try something. There's sometimes a tendency of being fearful of making mistakes. I don't want to try substitution because I'm not sure if it's going to work. Or I don't want to try integration by parts because that could be difficult. So you have to try something, and every time you try a method of integration, if it works, fantastic. If not, you've learned something along the way. So invest time into practicing, but as you're practicing, think about, why am I using a given technique? Why does it work well in this scenario? And that being said, our next video will explore several examples just illustrating some of these techniques. So stay tuned. Take care.